Well, hello everybody. I'm Charles Schultz, and this is the Randomizer. And tonight we're going to be talking about a little bit of an aeronautical subject, fluid dynamics subject, as a matter of fact. We're going to be discussing Stokes' law. Now, that sounds a little off the cuff, a little odd. Of course, all of these subjects are chosen at random, so it's as much a surprise to me when they come up as it is to everybody else. But we're going to have a lot of fun with it, and I've got some good examples that might pique your interest a bit. So tonight is going to be a fascinating discussion of something you probably never think of. Meanwhile, I am going to encourage everybody to go to schultzlaboratories.com or universesciencecenter.com. Click through to our live randomizer links at 6 p.m. Eastern Standard Time every weekday. And don't forget that tonight at 9 p.m. on Monday, we start lesson 1 of our new robotics class series, so it's going to be great. Be there for it. It's going to be a lot of fun. This is going to be one of the most interesting courses you'll ever take. Also, keep in mind that we need plenty more members to help our expansion, some of the things we're doing, some of the rooms we're adding. So become a member of Schultz Laboratories and Universe Science Center and help support what we're doing to add more galleries. If you're an educator or if you have a special skill and you want to teach everybody, contact us and we'll set up a gallery or virtual classroom for you to display your work and share your expertise with people all over the world. And I think you'll find that that will be a very satisfying experience. If you want to teach something, that's the way to do it. And I'll tell you, it's been said that if you want to learn something twice, teach it to somebody. So that's the best way to learn a subject sometimes. So let's move on with Stokes' law. So George Gabriel Stokes was born in 1851, and he was interested in many things. And you'll find that a lot of these people that I mentioned turn out to be kind of Renaissance men. They study many different subjects. Well, he was no exception. And one of the things that really piqued his interest was the drag from moving through a fluid. And that can be a liquid, it can be the air, it doesn't matter. So drag forces, what are they and how do we calculate them? Anything that you move through the air will experience drag. And if you've driven along the road and the window's open and put your hand out the window and you'll feel the breeze blow your hand back, you're experiencing drag. What's interesting is that when you drop something to the ground, if it were to fall on, let's say, the moon, that object would continue to accelerate, gaining speed as it fell until it struck the moon. But on the Earth, it's different. Although we have more gravitational force on the Earth, things falling on the Earth reach what's known as a terminal velocity. And that's because as they move through the air, it generates drag and it slows the object down. So terminal velocity isn't the velocity when you stop, when you hit the ground. What terminal velocity is when the speed that of your increase stops increasing. You reach some speed that you cannot go beyond because the force of drag from the air you're moving through is fighting back. So you'll reach a speed that is as fast as you can go falling, and then you will feel the normal force of gravity as you fall. That's terminal velocity. There was a group who did an interesting study years ago, and it was a group of skydivers, and they wondered if you were to skydive on Mars, what would you experience? And so they actually posted a page on the web called Skydiving on Mars. And they found that because the air is so thin on Mars, it's nearly a vacuum. On the Earth, we have 1,000 millibars roughly at sea level. On Mars, the air pressure is generally by the ground 6 or 7 millibars. So less than 1% of the air pressure we get on the Earth, and therefore much less drag. So here's the interesting thing. The gravity on Mars is about 38% of what it is on the Earth. So you'd think falling, you would fall slower. Not the case. Because of the lower drag, a skydiver on Mars will actually fall at 5 times the terminal velocity you'll have on Earth. This generates a lot of real challenges getting a spacecraft to land safely on the planet. So imagine dropping a spacecraft and it hits a terminal velocity of 600 miles per hour instead of 120 miles per hour. And that's just a rough approximation. But you know it's not going to end well. So they have to come up with an amazing amount of technology, such as retro rockets, parachutes, balloons, all sorts of bouncing things or accelerating or decelerating things, carriers that lower it on a cable and drop it to the surface. So there were real challenges because of the very thin air, even though the gravity was very low. On Titan, which has about 1.5 times atmospheric pressure, but it's all like nitrogen and methane, its gravity is only a couple of percent of what we have on the Earth. So an object falling to the ground can actually take an hour and a half, which is an amazing thought. So, how does Stokes' law come into this? Well, back in the 1800s, George Stokes was asking himself, what determines the terminal velocity? How can we measure the viscosity, the drag of a fluid? And by the way, even water has viscosity. If you move your hand underwater, you'll know there's a lot more drag than if you move it through the air. How does that affect the speed of a falling object? Well, physicists are very good at taking the simplest case. And so what he decided was to use a sphere, a ball, because it had the same cross section no matter how it might spin or rotate on the way down. That simplifies the calculations greatly. So really all you need to know is the mass of the ball and the force of gravity and the surface area of the ball, and then you can measure the difference in acceleration and drag and arrive at a viscosity number. That is the thickness of the fluid, how much it resists movement. Gelatin would have very high viscosity, and so would motor oil. And so as he thought about it, he realized that there was a very easy way to measure these things. If you have a column with some markers on it, you drop a ball in there, it's going to fall right to the bottom and you're not going to get much data. But if you were to fill it with a thick fluid, such as a motor oil or something similar, then you actually could measure with a stopwatch how slowly the object was falling. So he took it to himself to do a number of experiments, made a lot of measurements, came up with some equations. And of course, like all good mathematical equations, it has things like pi in it. And I'm not going to repeat the equation, but basically it says that the force of drag was equivalent to 6 times pi times the radius of the sphere times the fluid viscosity times the velocity that it was falling. So now he could measure the velocity and he knew the radius and he knew the force of gravity. He could work backwards and calculate that viscosity term. So it was a very interesting thing. He had an equation he could reverse and factor out the viscosity. And so we did measurements on many different fluids and came up with the verification of Stokes' law. And there are a couple of mathematicians who worked together. Stokes was considered a mathematician, not just a simple physicist. Navier and Stokes worked together to come up with a number of equations in fluid dynamics. Understand that if it's just a sphere falling, it's pretty simple to calculate. It's a minimal equation, as I mentioned. But when you get into complex forms and shapes, things kind of go off the rails. And this is because a complex form is going to rotate around until it reaches a stability position where it has the lowest drag, and then it's going to fall. And so you don't know what the incoming shape orientation will be to start with. But how do you calculate the drag on an irregular surface? So after Stokes' law was formulated, there were a couple of other fluid dynamic mathematicians, Prandtl and Tietjens, who came up with a whole handbook of integrals and calculus for doing all the really complicated behaviors. But what is the use normally of something like Stokes' law? Suppose you're a geologist and you want to know how long it took for a layer of sedimentary rock to occur, formation-wise, under a body of water. Well, if you knew the particle size, you could calculate its drag. You know the viscosity of water. And so this is an equation that can tell you how dense the particles must have been as they were coming down through the fluid and how rapidly they must have accreted and how much force they had. So here's an equation that actually can tell some geologists how rapidly a layer of sediment formed in the bottom of a lake. Wow, that's amazing. Here's another thing. Suppose you're dropping a depth charge and you want to know how rapidly that thing's going to fall. This is a war. You got to know how quickly it's going to fall, how deep it's going to go. How do you do it? You look at this viscosity figure. You look at the shape of your charge. You see how rapidly it falls in water, and you can calculate the time for it to reach a certain depth. You literally can set a timer for the depth that it will go off. Of course, you also have depth sensing switches these days as well. But it's something that could be used in military terms to determine how long it would take something to reach the bottom or some known depth. And actually, a lot of times when items were dropped for sensing on the ocean floor and they would freely fall through the water, you could calculate roughly how long it would take to reach the bottom of the ocean. So this is an equation set that's very simple to use if you have just a little bit of understanding of algebra. And it allows you to generate a whole table of numbers that you can then use later as a reference when you're doing other things that are practical in the real world. So one of the things that I find fascinating is the aerodynamic drag. And when you start figuring it, you ask yourself, as a skydiver, how fast am I going to be going when I reach terminal velocity? I was involved in a really interesting project a few years back. I believe it was 2016, when they had a fellow named Luke Akins who dove out of an airplane without a parachute at an altitude of 25,000 feet. Before the stunt was performed by the team that I do a lot of work with, I was asked, how much force of deceleration would you undergo if you were to free fall and then stop within a distance of 50 feet? Well, you have to know how fast you're falling. And if you're free falling flat on your belly, like a lot of skydivers do, your terminal velocity is about 120 miles per hour. And if you go head first, it can go much higher, 150 to 180 miles per hour. If you're in a wingsuit, it's a completely different animal. You can fall at as little as 25 to 100 miles per hour, depending on your angle, but you're moving forward at roughly 125 miles an hour when you do it. But on to the stunt. I wrote a spreadsheet using basically standard physics equations that showed if you were to fall at your terminal velocity at 120 miles an hour and you wanted to stop in 50 feet, the forces that you would experience would be about 8.6 Gs. So they made a huge arrangement with 4 cranes over 100 feet tall, holding the corners of a net with air cylinders to release it so the net would be moving when Luke Akins struck it. And he successfully did a dive from 25,000 feet with absolutely no parachutes and no backup. And we successfully caught him in the net and brought him safely to the ground. And that was the world record at the time. I don't think it's been broken since then. But that was one of the most amazing experiences I've had, where I had to do some algebra and some calculations. And basically, there was a human life in the balance. But I think that it was a very good demonstration of the solidity of the math. If you know the theory and you know the dynamics, it's pretty easy to do then. You just have to really grit your teeth and trust that your numbers are right. Fortunately, we did a lot of testing beforehand with dummies dropped from a helicopter that had force measuring devices in them. The numbers came out perfect. Here's another thing, the wingsuit thing. I was very privileged a couple of years back to go to the Ontario Wind Tunnel and practice in a standard skydiving outfit to float, fly, move around under the tutelage of Travis Feinhage. Now, he's 4-time world wingsuit champion, and I've done a number of projects with him as well, and he was a very patient man who showed me how to rise, how to dip, how to fall, how to turn, and it is an exhilarating experience. But it all comes down, again, to fluid dynamics. Once I got out of the tunnel, Travis did this amazing aerodynamic dance. He has mastered the understanding of drag and resistance and how to control your flight through the air. So it was an amazing experience and something that I'm never going to forget. So Stokes' equation has had some practical applications in my life. I don't expect it'll have a whole lot in yours other than flying in a plane, possibly skydiving. But it's something that I find interesting because of the dedication it takes for somebody like Stokes to figure out exactly how to calculate this and then formalize it to the point where we can use it all over the world in everyday applications in industry, in hydraulics, in geology, and landing spacecraft on other planets. So Stokes equation, an amazing thing, Stokes law from 1851, an amazing guy. So if anybody has any questions about fluid dynamics, the floor is open. And meanwhile, I am going to remind you, tonight, 9 p.m. and every Monday, Eastern Standard Time, our robotics series is now on. Go to the Schultz Laboratories page, click through and sign up for the class. Join us tonight. It'll be amazing. I'm going to teach you things you never knew. I'll bet you don't know how old the science of robotics is and how long robots, automated machinery, has been around in the world. It'll blow your mind when you find out. So, if there are no questions and nobody has sent us an email or a message and there's no text, great. I'm going to read my quote for the day, and it is this: confess your trespasses to one another and pray for one another that you may be healed. The effective, fervent prayer of a righteous man avails much. And that is James 5:16. Think about it. Something on your mind can just eat a hole in your heart. Get it off your chest, figure it out, and come to terms with it. And be healed. That's the way it is. So, join us tonight at 9 p.m. Learn about robotics. And join us every weekday, 6 p.m. Eastern Standard Time for the Randomizer, where we pull another technical term out of the ether, and we'll have a new one for tomorrow for you. And I hope you found something fascinating in tonight's discussion. And again, come to us with your questions, your submissions, any ideas and comments you have. Join us live on the air. We'll be happy to have you. Well, I hope that everybody has a great evening. I hope that you enjoy tonight and you enjoy your life and make the world a better place. This is Charles Schultz, and I hope you have a wonderful evening.